can't believe we're on Unit 9, Lesson 7 already, but here we are. Your anti-set is to use implicit differentiation to find dy dx for the curve x cubed plus 3x squared plus 3y squared equals 15. So we're first going to take a derivative with respect to x. We're doing d dx of this whole thing of x cubed, which is going to be 3x squared, times the derivative of the inside function x with respect to x, but dx dx is just 1, so we don't write. Plus, the derivative of 3x squared is 6x by the power rule times dx dx, which is again just 1, so do not write it. Plus, the derivative of 3y squared is going to be 6 times y times the derivative of y with respect to x, which we just write as dy dx. Right? What is d dx of y? It's just dy dx. Okay, and then that's equal to the derivative of 15, which is just 0 because it's a constant. And what we want to do is isolate dy dx because we are trying to determine dy dx. We want to say dy dx equals something. So we are going to subtract 3x squared and 6x over to the other side. So we now have 6y dy dx equals negative 3x squared minus 6x. Just subtracted those. And now we can divide by 6y on both sides. And we just get that dy dx equals negative 3x squared minus 6x over 6y. So this is an expression that will tell us the slope of this curve up here at any of its x and y values. We just plug in x and y, it will tell us the slope. Okay, so working more with dy dx today in implicit differentiation, just stop and think, which of these three will be modeled with this slope, with this dy dx? Well, kind of a trick question, because all three of these can be rewritten as 4x squared plus y squared, 4x squared plus y squared, 4x squared plus y squared. The only thing that's different is this number, right? And I can just show you this with one of these. If we multiply the whole thing by 4, that's going to give us 4x squared plus, what's 4y squared over 4? That's just y squared, and then it's going to be equal to 4. Okay? If we do this here, if we multiply this by 16, then we'll get 4x squared plus y squared equals 16. And then if we multiply this one by 100. And then if I take any of these and I differentiate, I'm going to get 8x plus 2y times dy dx equals 0. Okay, here I'm going to get 8x plus 2y dy dx. Sorry that that's black on black, but that's equal to 0. Okay, so it turns out that this number doesn't matter for the dy dx modeling the slope. What this number is going to do is it's going to determine the size of our ellipse, and we'll look at the three different ellipses graphically in a second here. But this dy dx is actually going to model an infinite number of ellipses, all with the same property of having the same ratio from the semi-major to the semi-minor axis. So this dy dx generates what we call a slope field, a new vocabulary word, a slope field, okay, which will show the theoretical slope of a curve at any given x and y value, okay, assuming that that curve follows the same properties as all these other ellipses. So notice this ellipse has a semi-major axis of 2 and a semi-minor axis of 1. So the semi-major is twice the semi-minor. And then if we look, and that's the one that goes with this ellipse. Okay. Now this one, this next one, has a semi-major axis of 4 and a semi-minor axis of 2. Right. So again, it's double semi-major axis in length. And then this other one, okay, it has a semi-major axis of 10 and a semi-minor axis of 5. So all of them have a major axis that is double the length of the minor axis, and any ellipse that follows those properties is going to be modeled by this slope, dy dx equals negative 4x over y. So what this does, what the slope field does, is it shows us all these infinite number of paths that could be modeled by this dy dx. So if we have a bigger ellipse, it'll follow one of these other paths, an even bigger one, or we could even go, between the black and the yellow, we could have another ellipse in here that follows these little slits showing the slope of the curve at each path, or at each point, rather. Okay, so for example, if a curve modeled by this dy dx has a point at 7, 5, what would the slope of that curve be? Well, we can just plug this into our dy dx. We get negative 4 times 7 is x over 5. So that's negative 28 over 5. So if we go to the point 7, 5, that's right here. And we can see that that slope is pretty steep, and it's also a negative slope, which is what we got here, right? So there is an ellipse out there that has a semi-major axis that is double the length of the semi-minor axis that comes through this point at 7, 5. And the slope of that ellipse at 7, 5 is negative 28 over 5. This will tell us the slope of any of these ellipses at any theoretical x and y value. Okay, so here's just that work again, negative 4 times 7, where 7 is my x value and 5 is my y value. Okay? And I could look at any of these points on this slope field and determine the slope of that theoretical ellipse that follows that path. So here's a slope field for hyperbola, multiple hyperbolas, that's modeled by the dy dx x over 4y. So let's see what we notice about this. Well, first of all, what's going on when y is 0? There's nothing there. So y is 0, and we don't see any kind of slope there when y is 0, because if I do x divided by 4 times 0, well, that's going to be an undefined slope. So whenever y is 0, there's no slope showing up because it's undefined. All right. What about when x is 0? That's following. This is all the places where x is 0, and we notice there that those slopes are flat. Okay, they're just a horizontal flat line, and that would make sense because if I do 0 divided by 4 times y, that's going to be equal to 0, so that's where my slope is equal to 0, right? Notice that as x gets bigger, the slope seems to get steeper because that's making the overall value bigger. That's the numerator. As the numerator gets bigger, the slope gets bigger. What about as the denominator gets bigger? As y gets bigger, it seems like that slope flattens out, right? Because that's making the denominator bigger. So we can see how changing x and y affects the slopes of the hyperbola that follow this kind of path. So here's a couple of them. Notice that it doesn't matter if it opens vertically or horizontally. It can still be modeled by this slope. And again, that comes from the fact that if we multiply through by 16, we're going to get x squared minus 4y squared equals 16. Okay, or we're going to get 4y squared minus x squared equals 16. And if you take the derivative of these two, you should arrive at x over 4y no matter what. So it doesn't matter if it opens vertically or horizontally, it can still be modeled by this slope. Just notice that the one that opens horizontally is more squished in, and the one that opens vertically is more flat. And then obviously there's an infinite number of hyperbola here that could be modeled by x over 4y, again just following this same property where this number is 4 times that number. This number is 4 times that number. So yeah, let's think about what are these in parametric form. Try to go from this form back to parametric form. So I can do this for one of these. We know that this is secant squared minus tangent squared, and that's equal to 1. So what's secant squared equal to? Secant squared is equal to x squared over 16. Okay, just lining these up, right? Secant squared goes here, tangent squared goes here. So then if I solve for x, I'm going to get 16 secant squared equals x squared. And then if I square root both sides, I'm going to get 4 secant equals x. So that's how I can determine what x is, and I can do the same thing for y and tangent squared. Okay, so I get x is 4 secant, y is 2 tangent, or x is 4 tangent, y is 2 secant, right? Recall from the last lesson that if I take dy dx of these two, I'm going to take dy dt and dx dt, and what that's going to do is I'm going to get, when I do dy dt divided by dx dt, I get dy dx, I'm going to get a 2 coefficient over a 4 coefficient in both of these cases, because dy is going to have a 2, dx is going to have a 4, dy has a 2, dx has a 4, right? So that's why we see that the slope approaches plus or minus 1/2. So if we draw these asymptotes, we can see that no matter what kind of hyperbola we have, it's always going to approach that asymptote. Even ones way up here, it's going to take them a long time, but eventually they're going to approach that asymptote of plus or minus 1/2. So this is looking kind of messy now because I drew a bunch of these on here, but all of these all of these hyperbola follow this same dy dx. If I plug in one of their x and y values, it'll tell me what the slope is at that point. So now we're going to do some more challenging implicit differentiation, but I'm actually going to do this on the next video, so we'll do this in part 2.